take PhD here in CISA, where at that time we started to use supercomputer to do science. And in the last 20 years, we have seen more and more computers, and especially supercomputer, become more and more relevant in science first, but then also in technology. Let's say supercomputing, one may say it's a sort of computer in steroid, and sometimes we, let's say, compare supercomputer and computer like Formula One, for which we intend supercomputer, and computer like a normal car, okay? But this is not exactly true, because if you take a Formula One, this is twice as fast as a normal car, probably. But when we speak about supercomputer, these are thousands and sometimes hundreds of thousands faster than a normal computer. So this is the scale that we can access with supercomputers. So it's a sort of time machine that allows you to use technology in a sort of future, because you can see what will be the power of a computer, of the computation in the future. So this is, let's say, why supercomputers are transforming our society, both in science and technology, and now, thanks to the computing power they reach, are also transforming international relationships. So now supercomputing is becoming the new space race. So there is, let's say, different blocks in the world, mainly in Asia, US, and Europe, that are racing to build the most powerful supercomputer in the real future. And why that? Because everybody is now convinced that supercomputer is triggering a disruption. So the power we can reach is so high that really we cannot, let's say, we just not accelerate what we do elsewhere, or in different way, but we can start to trigger disruption. So do different things, not do the same thing faster, but do really different things. So today we will speak with three guests about, let's say, and listen what is the story about this transformation going on, both in science, different aspects of science and technology, and how important would be the use of supercomputer and in general the computing in their business for today and for the future. So it's a great pleasure for me also to introduce our guests, which are Elisa Molinari, Roberto Chingolani, and Eric Lindahl. I'm going to ask them to introduce themselves, but let me say that it's a great pleasure to have these three guests with me, because sort of my recent career had something to do with each of them. So with Elisa, we started more or less six years ago, a center of excellence in computational material science, sort of crazy thing to folk 6 years ago, because not everybody was convinced that it was so important to have, let's say, a dedicated center for specifically for improve the computational part of the science, not the science itself. Then we will have Roberto Chingolani, which now is a colleague, and Roberto is a CTO of Leonardo, and he as well, he was so crazy to ask me to join Leonardo and become the director of HPC Center there, which we are building in Genoa, to the other side of the peninsula, Italian peninsula. And finally, with Eric Lindahl, that believe it or not, at the end of the last year, in December, before all the COVID-19 start, we wrote a project to fight pandemic. That's an incredible story to tell. We were sort of anticipating, and then we were able to, let's say, wrote a project, but also start to develop the software to find, let's say, drugs against pandemic. And now I think they also are obtaining good result, and maybe Eric will tell you about the story. So let's first start with Elisa. I would like to ask Elisa to introduce herself and listen lively from Elisa what is the role of supercomputing in her everyday business as a scientist and professor at university.
Morning, everybody. It's really a pleasure to be here. Actually, my personal story and how I came across HPC comes from far. I started out with an interest which was very much on fundamental quantum physics. I was coming from classical studies. I was interested in more in the philosophical aspects of all of that. And essentially, one of the fascinating questions that I came across was how comes that all the uncertainty and probabilistic aspects associated to quantum physics then can bring us to learn something and predict in a deterministic way somehow what happens in real life and in real matter, physical matter. And the answer was found, of course, when you start studying quantum physics and what we teach now in quantum physics in my university and so on. The answer is that you are able to study the deterministic evolution of the probability associated to what some particles do. And there's an equation, Schrödinger's equation, and some other evolutions after that allow you to predict what happens to the cloud of probability that describes the behavior of an electron or many electrons in matter. So in principle, that was the starting point, and apparently very far from supercomputing. But it happens that if you want to really use all this, it's not having the equation that brings you very far. You need to be able to treat complex systems which are untractable in simple analytic ways. And you need to, except for small systems, you really need pushing computing and supercomputing. And so we started getting very interesting questions in science and also in technology, how a device works and so on, and trying to use all those tools for understanding. And it turns out that having quantum mechanics as a tool is really crucial for some phenomena, because if you just treat particles as if they were macroscopic billiard balls, you're not able to treat all those phenomena where the electronic cloud modifies, you get interactions and so on. So it turns out that this really opens new way in the predictivity in understanding systems for which you don't have your experiments yet. So I got more and more interested also in the applications. And I think Freeman Dyson, a great physicist, was making a statement which I find more and more true as I grow old. And this is that scientific revolutions people used to think that they were driven by concepts, and this is of course true. Quantum mechanics was the concept, maybe, but they are also very much more and more driven by tools. And you wouldn't have nanoscience if you wouldn't have the experimental tools to understand. But nowadays, you wouldn't have these paradigm shifts that leads to predicting materials if you wouldn't have the tools, which are our computational codes that allow us to use all this supercomputing power that Carlo was introducing. So I'm actually a professor of physics in a university in Modena, and I'm associated to a physics institute of the National Research Council, which does fundamental research in nanoscience. But I also got more and more into this idea that we needed to join forces with other leading teams in Europe to build a center of excellence, so-called. Actually, excellence you always have to demonstrate a posteriori, but okay, Europe launched this idea of centers of excellence where we develop the tools that allow people to use fundamental quantum mechanics to predict the matter and materials properties of the future. that's how I came to it.
Okay, thanks, Elisa, for this introduction. Then I would like to ask Roberto to introduce himself as a CTO of Leonardo and former director of Italian Institute of Technology.
Yeah, good morning, everybody. Thank you, Carlo. Look, my story is possibly not very standard. I'm a physicist by background, and I started with material science, semiconductor physics, quantum heterostructures, quantum devices. I was a professor in the university for a dozen of years, during which, pretty much like Elisa, and I was sharing a lot of research with Elisa too, I was very much interested into the very deep properties of new heterostructures, quantum phenomena, and so on and so forth. But I resigned at a given point many years ago, primarily because of my passion and drive towards technology. And I was in charge of funding and directing the Italian Institute of Technology, which is a public research institution. Actually, in IIT today, there are about 1,800 researchers, about one half are coming from more than 60 countries. And this institute was dedicated to three main research areas. And this is very likely, this is the reason why I came across with HPC in a very intensive way. The first area was artificial intelligence and robotics, and there were a plethora of people working on deep learning, machine learning, artificial vision, augmented reality. And there, it was primarily a matter of computational power versus quality of algorithms. It's interesting to see, if you read the story of AI, between the 60s and the 70s, there was the so-called winter of the AI. Actually, there were fantastic algorithms, but there was not enough computational power to solve them. And those algorithms were otherwise not analytically solvable. So AI was in principle much more developed than exploitable, primarily because there was no computational power. When we started our humanoid robotics activity in IIT, computational power was high, but in 10 years, it became by far higher. And we could see how the progress of the intelligent autonomous system happened just because of this very important change. As Elisa said before, tools matter, not only principle in this case, tools are very important. It's pretty much like Formula One, because I like the concept that Carlo introduced before. You need a good pilot and you need a good car. Let's say in this case, we are talking about the good car. In this case, the tool is very important. Then you need very good software, you need very good scientists to exploit this incredible power of the machine. The second line in IIT was smart materials, so materials by design, composites, where you can tune the chemical, physical, mechanical properties, thermal properties, by inserting quantum structures, fibers, very small objects, very similar to doping in semiconductors, but with a much more sophisticated technology. And there, the possibility to design the material, so to simulate the material before spending your time in trying and retrying was an incredibly powerful enabling technologies. There are two ways. You try and retry every day, you waste material, you waste time, you waste money, or you simulate, and then of course you have a very intelligent shortcut towards the intelligent material. And the third line was drug design. There was a massive investment in HPC done by the Institute to design drugs. And I think these were the three areas that the Institute developed, and all of them were strictly interconnected to HPC. Lately, after about 15 years, I moved from IIT and I started this last adventure. Today, I'm the Chief Technology Innovation Officer of Leonardo. Leonardo is an aerospace company. It's one of the largest in the world, 50,000 people, 14 billion budget, so it's quite large. And at the moment, I have to handle the transition towards the digitalization of the company. I have about 10,000 engineers, and I can tell you in a very synthetic way, talking to all my engineers, that they built aircraft, helicopters, satellites, very difficult, big things, but they all need AI in manufacturing, digitalization of the engineering, simulation and control, with very advanced tools, big data analytics for the immense amount of data that aircraft, helicopters, satellites produce that are hardly analyzed normally. So actually, I think HPC in combination with the data analysis, even in the company, even the high-tech company, is becoming the new paradigm for the future technologies. And this, I stop here for the story, and maybe afterwards I will give you more examples about those activities.
Yeah, thanks, Roberto. Then, last but not least, I would like to ask Eric Lindahl to introduce himself.
Thank you.
Okay.
Will do. I think I have the benefit of life science. I'm actually going to show 2 slides or 3 slides. So it's great to be here, and too bad that I couldn't join you in Trieste, in particular now in fall when temperatures are getting lower.
Sorry, just because maybe it's interesting that I have to say that the room is full here. Now I feel more comfortable, and let's say I feel the heat from the public. So it's nice to be here again with a lot of people in the room, and maybe much more from remote. This is probably a new paradigm to have maybe more people involved in this kind of event.
I think we're going to get better, but I'm very much looking forward to see all the people too and have dinner together. So my background, funnily enough, my background is actually quite similar to, say, both Elisa's, the rest of you. So I too am a physicist by training. And I think there's an important story there to go into. And I'm going to tell you a little bit about this odyssey that I've had the benefit of enjoying the last 2, almost 3 decades. So when I was a PhD student, the hardest part in my life was actually deciding whether before my PhD studies, whether I should go into life science and medicine or hardcore physics, mathematics, and computers that I also loved. And I ended up in computer and physics, but it was probably like tossing a coin. But I think chance has a way of working things out for you. So later on, when I started my PhD training, I ended up working on molecular simulation methods. So not what Elisa is doing. So I'm actually doing these hard balls, not bothering about the electrons. Because in life science, in contrast to, say, materials, most of the things that involve, say, your proteins in your body, say, skin, hair, ligands, receptors, they don't require us to break bonds. And then, surprisingly enough, it frequently works really well to work with balls. And in contrast, I can reach much longer timescales. But when I was a student, this was like something the cat dragged in. Nobody was interested in this. And thank God we got a little bit of funding. Obviously, this is never going to lead to any applications. Although the moral of the story here that I was fortunate enough to enter this field at a time where we started to be able to do better and better simulations. I grew frustrated with how slow the software was in particular, so I ended up writing a lot of the software. And then I was also lucky enough to have friends all over the world that gave us access to supercomputers at the time. And by supercomputer, I mean something that's way slower than this by today's standard. But as these simulations grew faster and faster, suddenly everybody doing experiments got extremely interested in this because they realized that they could actually understand things in the lab using the simulations. So I'm not really sure how it happened, but my career somehow transformed from being a dusty bookshelves in a theoretical department to joining biophysics labs all over the world, doing great postdocs at Stanford, Pasteur. And today I'm a professor of biophysics, and I even run a fairly large experimental part of my team too. But the moral of the story here, it's very hard to predict success and applications before we see it. Today, it's almost impossible to publish a high-impact paper on, say, a structure of SARS-CoV-2 proteins, for instance, without also having done simulations on them. And what started out as a small code that I and some fellow PhD students wrote is now one of the most widely used codes in the world. I think people use 5% of the world's supercomputing time just for my code, which is on the one hand humbling, but also deeply satisfactory, because I think we all are in science because we believe in what we do and we like to be able to help other people. And no matter how tired I am on a Friday evening, this gives me a deep feeling of satisfaction that we are actually helping other people. And just as Elisa, we've then benefited tremendously from the European Union initiative of these centers of excellence and actually being able to hire and give younger people careers to maintain this. Now, what you see on the right there is actually a simulation that 2 students in my group then started. And believe it or not, this is now also generating spin-off companies. In this case, to understand how drugs penetrate your skin. And if you had told me that 25 years ago in a theoretical physics department that we would have spin-off companies, I would have laughed at you. But again, it's very difficult to make predictions, in particular about the future. Now, what we've been doing the last few years, and I think we're all going to come back to this a bit later, that this is not just a one-way story. It's not just simulations conquering experiments, but all these fields that used to be extremely experimental, such as determining structures, that used to be a 4 to 6 month endeavor, and it's extremely difficult. But as you might have seen the last few months, in particular with COVID, the determination of some of these structures was done in 2 weeks. And the reason why this can happen in 2 weeks is that people, and again, my team has been able to make some small contributions here, but work that was previously done in the lab is moving to computers, because computers is enabling us to study tens of thousands, hundreds of thousands, or even millions of very noisy particles, and use computers to really reconstruct the structure of a protein, such in this case it's an ion channel, but also all the SARS-CoV-2 structures have been determined with cryo-EM. So this whole traditional divide between theory and experiment, really, it doesn't exist anymore. Everybody in the lab is using computers and data, and those of us who used to be theoretical physicists like Elise and me are now very much working in applications. And I guess that's kind of the story of my scientific career too. I'm still not really sure what to call my subject anymore, but over the years, I've come to love that. Science is usually most fun when you're in the white spots on the map. And this is very much a white spot on the map for all of us. Thank you.
Thanks, Eric. Just to say that before joining Leonardo and when I was, let's say, in Cineca, I was as well a developer of a code that is now part of the Max Center of Excellence, and the code is born here in Trieste, so it's a pleasure to me to remind that this is Quantum Espresso, which fight with GROMACS to consume a lot of cycle of supercomputer. So if we can, let's say, continue the comparison with Formula One, we are actually fighting for the same seat on the machine, on driving the machine.
and to the Italian audience, if there's anybody there listening, CISA is possibly the best scientific investment Italy has ever done. It's probably not seen as an exceptionally applied thing, but it has had more impact than most other programs, I think.
Yeah, thank Eric for this remark, and yeah, I believe so. I think it was for me really important to study here in CISA and to learn many years ago to start use computer, which is triggering transformation, as you said. So continuing along this line, I then would like to ask you, then I start again from Elisa, which are the transformation supercomputing is bringing not to your career, but to your field, and at the same time, how is, we already mentioned that. So computer, if you take computer, supercomputer as well as computer, they are silly things that have billions of small switches that continuously flips between 1 and 0. So this is what essentially a supercomputer is. And the faster is the supercomputer, the more you have these switches. So alone, they will produce only noisy ensemble of 1 and 0. But what is determining the power of supercomputer is also another really important component that we already introduced, which is software. So the question is how supercomputer is transforming your field, and what kind of software, or what are the transformation as well that you have to do in your, let's say, skills. So what kind of skills are needed to be physicist, biochemist, engineer, and at the same time being able to drive this fast race car, which is a supercomputer. So Elisa, Tell us what is your story about this concept of software and transformation.
If you ask me where is the impact in what we do, just imagine we are working on simulations of materials, what we call these first principle simulations of material, where, as I said, we use quantum physics to understand them. Materials are basically enabling the technology and the science of any physical object. So basically, they power our economy and society and manufacturing in a very pervasive way. If you think of any physical object, a chip in your computer or in your cell phone, or also or even those which will be in the future quantum computer, the implementations of real quantum computers, the disks where you save your data, the technologies for energy that are needed to power it all, the ones for harvesting, photovoltaics, the ones for storing, the batteries, all that. All the manufacturing, all this involves materials. And understanding materials and designing materials, as was anticipated, if you can do it by, if you think of Edison, he was trying to, in order to design his filament, to find his filament, was trying in the lab for years, thousands of filaments. If we can do that by simulating all the components of these devices and the materials that form all these devices, and we can basically interpret and design properties from conduction to the color of material, their physical appearance, their biocompatibility, their thermal conduction, and so on. If we can do all that, we are basically modifying completely the way we work in the lab, in the labs. Not to say that experiments disappear, but we have an automated cycle of interaction between theory and experiments, which is really changing the world. So and it also induces new questions for science, as I must say. A lot of very exciting questions concerning the interactions of particles in materials, how dimensionality and topology affects that. There's a lot of very exciting science coming about in all this technology. Now, think what happens if you can design these properties in a predictive way and doing it in a high throughput way. So doing many explorations of materials, and then out of that, without having to try the thousands of filaments as Edison was doing, out of that, it identified the interesting cases, it identified even the interesting concepts that can drive your materials design and bring that into the cycle. So this is what we are doing with our codes, and this addition of high throughput and data is becoming more and more important. What do you need for that? You need people who are top-notch scientists, so who know and like the science, but you also need them to become able to talk with computer scientists, with experts in computing, with people who work in the supercomputing center. You need a completely new way of training people where all these tools become native. I mean, people must become able to use them and in a way that is not the way I learned later on how to program and how to use the computer as a tool. So this is happening, actually. This is one of the big advantages of this, for example, Center of Excellence operation, getting so many people involved in younger people and getting also a big effort and a big support in doing summer school training events, working with PhDs, and we hope more and more also with master students. We're starting that. So it really requires having the codes as a value in the training of the people. People must be praised if they work on an open source code which becomes available, as Eric was suggesting to the whole community. It wasn't like that in the past. We were commenting earlier with Roberto that in the early times when we were collaborating, I was hiding the work on code development or on method development when we submitted proposals. So the proposals were for getting your final technology or your final research funding, but the work that you had to do to develop those tools was hidden, and there was not much advantage for a young person who would invest in developing a code for the benefit of everybody. I think now this is already somewhat changing, so we're getting funded for developing the code and not just, or the training and so on, and not just for, and the codes are a value. And I think this has much to do with HPC, I must say, because if you are leading in a code development, you are also interacting much more closely with the development of hardware technology. It's what is now called co-design of hardware and software. And our codes, Quantum Espresso, for example, Yambo, others that are actually important pieces of codes developed in Italy, but we also have many others in Max, Siesta, CP2K, many others. All those codes are themselves a value, and they are benchmarks in when a supercomputing center all over the world wants to buy a new supercomputer. And in some way, they also contribute to designing the way we can take advantage of HPC technology. High-performance computing is nowadays very much driven by things which is not science. Sometimes they are driven by computer graphics, they are driven by workstations, by things which are not necessarily what our needs are, but we can work with developers of the hardware to get it most useful to develop, to be able to do our science with it and our technological applications. So I think the future of this part of code development is very much in the people and in getting the people trained to do this type of things in this way, interacting with other disciplines and especially with computer science-centered disciplines.
Thanks, Elisa. This is a very interesting concept, and this was a radical transformation we were testifying in the past, because myself, I remember many years ago, there was, this is my code, well, this is all my work, nobody else, I don't want anybody else to steal my precious work. At a certain point, the code started to be so complex that myself, I start to say, well, okay, if someone is able to read what I wrote, he deserves the code itself and to use it, because it was so complex, so useful, so hopeful in terms of engineering that it was, let's say, almost impossible for other people to take a code wrote by a bunch of scientists without training, proper training, without engineering, and use it fruitfully. So I would like to ask Eric, which is, I think, one of the nowadays world leader in a community-driven development, what you think about this transformation, and as well, what are the other transformations you see in his field by the use of supercomputing and by this new way of developing code, and what kind of skill are needed in the field. So Eric, please.
Oh, those are lots of questions. I'm actually going to start with a bit of an analogy here. So some 20 plus years ago, Sweden and Finland were obviously world leading in telecommunications. We had Ericsson and Nokia, and they pretty much split the entire world market between them, right? The only thing they were worried about was the Chinese. They might start doing hardware. And as you all know, what then suddenly happened, in particular on the handset market, that we had two companies in Silicon Valley, Apple and Google, step in and steal the entire market. That is not because they made better hardware. That is because they understood the value of software, and it's an ecosystem around it. Now, one can certainly worry about that in telecommunications and everything, but when it comes to supercomputer, Europe owns the software. We are far ahead of the US and we are far ahead of Asia. I'm not exactly sure how it happened, but this is something that we should be remarkably thankful for. Because when it comes to hardware, we all change that hardware architectures every few years. But as a scientist or company, the one thing that you tend to stick with is the software, because the software is your strategy. I'm not just talking about the specific code, how to run something, right? But my entire strategy, whether it's a company or whether it's a pharmaceutical company or doing materials design, my strategy for how to design things, the data I use and the type of calculations I use is far more strategic than the hardware. We adapt the hardware to the software and strategy. Now, the challenge there is that most of these softwares came from people like us, theoretical physicists, that we probably had 5 weeks of training of programming when we started. And what has changed, as we heard, is that the softwares have gotten so much more complicated because the hardware is getting complicated, that we all need professional or semi-professional people developing them. So you asked this question at the start, who should be developing this? I know it's certainly not physicists, but these are increasingly software engineers trained in high-performance software engineering. And it's a career, we don't really have any good traditional career tracks for them in academia. It might be better in industry, but it's potentially one of the most valued categories of people we educate. It happens every 2-3 years that I lose one of them, and then that's because they get a 3 times higher salary in industry than I can offer them. And as much as it irritates me, I'm also very happy for their sake. The single best decision we made here was that we got to the point where we simply couldn't keep track of, well, trying to fix bugs and doing everything. So at some point we realized we might as well give up, open this up, make it open access, allow anybody to steal our code, which we went through very much these things that you said, that nobody can touch my precious code. They're all out to steal my code. And what you very quickly realize that's not the question you should ask yourself. The relevant questions are, you should be very thankful that there is anybody who wants to use your crappy code, because it's full of bugs, it's undocumented by industrial standards. They were pretty bad 20 years ago. But what's magically happened when we turn these things into worldwide communities, there are people helping. There are people helping everywhere. One of the best people that we had was a guy in Australia, and he was sitting and answering mailing list questions, fixing bugs all the time. And he was so good, so eventually we offered him a job. We offered him a job without ever having met the guy. And then he moved to Sweden, and now he's worked with us for 6 years. And I think this is the impact we're seeing, that science develops better, faster, and more efficiently. That it is humbling here too, right? Because if you put things out in the open, people will point out that, sorry, Eric, you made a mistake here. And 2 of the papers you published recently are actually influenced by this. And yes, that is embarrassing. But the only thing that's more embarrassing is, of course, if nobody points that out, because then I will keep making the same mistakes in my publications. We will have the startup that I talked about. They're going to keep using my mistakes. So pointing out mistakes early, open, that is ultimately what builds value, both in science and commercialization. And right now, I think Europe is insanely good at this. These codes are driven by Europe, they're funded by Europe, they're frequently predominantly used by Europe. But the mere fact that we're open to Asia and US too, that is what kind of gives us, I wouldn't say world domination, but very large worldwide influence here. So we've done really great. We should just maintain this.
Thanks, Eric. Now, then we have listened about what is happening in science. Now I would like to ask Roberto instead, what is the same impact, but looking inside what is a company. So in terms of transformation, about the use of computer and the aspect related to the skills that are needed to write software, and well, as we know, we cannot be so open as it happened in science for many different reasons. So we here try to listen from Roberto what are his problem as he are fighting inside the company. Roberto, please.
Okay, let's say we don't have problems, we have solutions. Come on, we have to be optimistic. I think that there is a very interesting example for a non-technical audience in the specific aerospace market, for instance. It's a very interesting example that explains what's going on. You know, if you consider the strong manufacturing companies, you have the information technology and electronics that is normally rather fast. Let's say products are developed on a time scale of 1 or 2 years. Then you have the automotive area sector, in which products till a few years ago were released every, let's say, 10 years. So the pace of the product, the technology was in the range of a decade. And then you have the aerospace, where normally the product lifetime cycle is developed over about 40 years. This is the lifetime of an aircraft, typically. Okay, things now are changing completely, primarily because digitalization is much faster. You can design a product, you can simulate the behavior of a product on a much shorter time scale. So what happens is that information technology deliveries occur every 6 months. Cars are renewed every 3-4 years. And cars are now tackling the market of aerospace. For instance, Hyundai made an agreement with Airbus for a flying car. Aston Martin with Rolls-Royce. Rolls-Royce it's a producer of aircraft engines. Porsche with Boeing. So this is moving towards a 3-dimensional traffic. That means a swarm motion. That means a 3-dimensional control of traffic. You see, these things are really disruptive, and in the future, that will change completely the market. So what happens to an aircraft or a satellite builder? Of course, we are somehow undergoing this change, and we have to face a real revolution. I think one of the benefits that we can get out of the HPC investment is that today you need 3 hours to simulate the very complex fluid dynamics around the wing of an aircraft. Until a few years ago, the same simulation would have taken 3 weeks. This means that you can be extremely much faster and more effective in designing a complex system like, for instance, an aircraft. So what is the target in the short term? We want to accomplish digital twins of all our technologies. That means you need to have the digital avatar of any complex system. This could be an helicopter, an aircraft, a satellite, whatever you want, but you need to have the full digital description of this technology. And this would open completely new landscape for the high-tech companies. Just to give you an example, design becomes much more precise and much faster. You don't touch a piece of material, a screw, you don't touch any manufacturer until you have the full digital design of your product. That is a very important point also in terms of sustainability. Don't forget that manufacturing companies are using water, using energy, using raw materials in their sort of primitive approach to construction. So try and retry, progressively improve by empirical test. If you can really exploit advanced digitalization of the design, so having the digital twin of all your technologies, you don't waste energy, water, material, but for the computation. And of course, the company automatically gets more effective and more sustainable. A second issue that is extremely important, especially in aircraft, but also in, for instance, in the pharma, is certification. Many products, they have to undergo very deep and complex certification procedures. Don't think you can change a single screw in an aircraft without undergoing a complete certification program. And this means that you have two possibilities. The first one is that you build a sacrificial aircraft, you make the test, and if the test is successful, you get the certification, or you have to build another one to improve the result till you get the certification. This is awful, but this is the way it works so far. The other way is that you make everything digital. You can test any scenario, you can test any change, and this is an extremely effective way to improve certification and safety. The third level is training. If you have a very advanced digital twin, a digital description of your system, if you have augmented reality in a proper way, you can make training for pilots, for users, which is much more effective than, for instance, driving an aircraft or flying with an aircraft for 100 hours before getting the patent for the pilot. A fourth level is maintenance. And in general, you have to consider that so far we had to train operators for complex systems such as aircraft or helicopters acting on the machine. And this is very expensive. It needs physical presence. It needs machines that are dedicated only to maintenance, to training and maintenance. Whereas now you can do most of this by augmented reality. We are developing augmented reality maintenance systems that are incredibly effective. You wear your gloves, you wear your system for augmented reality vision, and you operate in full immersion without touching physically the system. So you can make maintenance in augmented reality at distance. And finally, the fifth level, I'm sure that not everybody knows this. Any aircraft, any helicopter, any complex system which is flying produces terabytes of data, continuously updating about the status of the sensors, the flight status, and so on and so forth. Those data normally are not analyzed. They're just kept buried into a data lake, and they're not used unless there is some specific problem, typically an accident. Now, having performant HPC machines and big data analytics allows you to analyze those data in real time, transforming maintenance in something predictive. So imagine, instead of saying every 1,000 hours of flight, you have to come to the company and make your assistance program, having an intelligent system that tells you when it is necessary to make your maintenance, which is only when it is necessary, depending on the state of use, conditions, accidents, and so on and so forth. So ultimately, what I want to tell you is probably what will happen in the future is that very complex technologies like aircraft, helicopters, satellites will be rent, just like mobile phone. The business will not be the aircraft itself, but it will be the ensemble of digital services that we will sell over the 40 years of lifetime of the product in terms of maintenance, training, control, simulation, and so on and so forth. And this will be pretty much like in the digital company, a large part of the future product, of the future business. You understand that the HPC, together with big data, so together with the large storage, is the driver of this product transformation. And this driver is very important also for sustainability.
Thanks, Roberto. Maybe you touched the important subject of artificial intelligence. Maybe it's worth to remember that, well, we speak about the supercomputer, and many people speak about artificial intelligence or big data, maybe without combining all these three terms together. But actually, we know all the professionals that work with supercomputer know that they are intrinsically linked together. So it is not possible to develop today, let's say, performing artificial neural network without having a supercomputer or very fast hardware to train the network and a lot of data to be used as a test for the network itself. So it's really, let's say a transition that, as has been already said, it has been a transition enabled by the supercomputer, the fact that today we can use and we can see, actually all of us can see that artificial intelligence is already changing our life, because continuously we are, especially now with the lockdown of the pandemic, we are more and more interacting with machine rather than with human, because we are continuously using digital devices, a mobile phone, ask things, receive, respond. We are continuously interacting with things that try to adapt to our behavior. So this was a transition that was fundamentally enabled by the power of supercomputers. So now, for the last round, before of let's say opening the discussion to the public, the last round of question is now about imagining to have the crystal ball. So now we speak of what the supercomputing has changed today. As I said, artificial intelligence is a great example. It was a disruption enabled by supercomputer, but I'm almost sure that artificial intelligence is just one of the many transition and disruptive transition that the more and more computing power that we can have in our hand, just because also there is maybe another transition that is worth to remember about, which is related somehow to supercomputer, which is the possibility to access faster and faster resources on cloud. So at the beginning, cloud, you can access resources just to write HTML pages, load a web portal, and so on and so forth. But today, the main business of Azure, Amazon, is not to build the cloud for the host portals, host web pages. But the large business is to host systems that are rented for let's say, developing new algorithm and develop and train a new neural network. So they are actually buying and improving cloud's resources with a chunk of supercomputer. So following this example that we are seeing right now is not in the future, it's what is happening today. Try to have the crystal ball. I would like to ask our guest to imagine what is I know Eric already said the future is unpredictable, but just let together do this kind of, let's say, exercise and take our crystal ball and look what is the next disruption in your field that can be triggered by the use of supercomputer in combination with maybe some disruption in the software side. As we said, the software is as important as the hardware. So this combination, as it happened with the artificial intelligence, what can trigger in your field? So Elisa, again, it's your turn. Look in your crystal ball and tell us what you can see in 10 years from now, coming to material science and computational material science.
I must say I agree with Eric. Anytime I made predictions, I saw them overcome. So we are very often too conservative with our predictions. So I must say, in my vision, there are big open issues that we might be able to solve, but I'm sure there will be more. Just take one. Think of photosynthesis in nature. Nature works in a much more efficient way than we can do in any artificial system in the overall process of converting energy from sunlight into usable energy, and we are still very far from that. I think we need a lot of science and understanding, but also a lot of computing and a lot of quantum mechanics, quantum physics-based work in order to figure out the concepts and the principles and being able to simulate and design artificial objects that are as efficient as any plant that I see out of my window. And if I think of, and this is one, but examples where actually we basically probably will interface our science and tools with those of biophysics and biomolecular research. But there are many other. I think batteries will be one of the places where we can make a difference. There's a big European initiative now, which is called Battery 2030 Plus, and also some big map, so-called precursor to it, where people try to integrate automated design of the materials with the physical realization and the automated spectroscopy and characterization of materials, much more of close integration between what we can design, predict, our computational spectroscopies, computational microscopies, and what can be done also in an automated way in the lab, in large-scale synchrotron facilities, and so on. I think there will also be a lot of computers helping to design new computers, quantum information, the tools for quantum computing and quantum information, or for future emerging ways of computing that we don't know now. I think all this growth, this amazing hardware growth that we have seen is changing its pace, and we know that there will be some disruptive technology becoming useful, and I think we can help designing all that. So from the point of view of what type of systems I see, because that's what's closer to my knowledge, much of the energy and much of the information technology developing, and all the mechanics and stuff that Roberto was talking about, that's more on a larger scale. We will have to interface on all scale. I think multi-scale is also going to become a very important keyword in the simulation. From the point of view of methods and approaches, I think open source is going to be the way, involving large communities into the developing of software. I think it's very crucial, and that's changing the way we all work, and I'm very much in favor of that in software and probably also in hardware in the future. And I think much more also of critical awareness of where these technologies are taking us. I hope this is something that is going to be more and more integrated as we go along with the use of high throughput, artificial intelligence, and all type of computing. Have more and more people that start with the science and scientists and technologists to think about where are the challenges, the risks, the perspectives, and getting all this much more interconnected than before.
Thanks, Elisa. Now it's the turn of Roberto to take your crystal ball and look at what will be the impact of use of this extremely useful technology in 10 years from now, with the perspective of a large industry.
So, Carlo, I think this goes a little bit in the direction of the strategic plan of Leonardo for 2030 that has been accepted recently by the board of the company. But I think it's a general transformation trend in most companies worldwide. Companies are active, of course, in high tech. I do foresee 5 pillars that are very infrastructural. Honestly, I can't see how a high-tech company could survive in the future without having an infrastructure for high-performance computing, a powerful cloud and data analytics capability, a very wide use of artificial intelligence in not only in the design but also in the manufacturing. I will spend a few words later about this point. And of course, these 3 tools should be combined with the availability of a very efficient 5G network. This is, of course, not responsibility of the company, but should be provided by country. And an extensive and effective fiber network or fast network, not necessarily fiber for the connection. I think that then, depending on the core business of the company, having those tools and having those public infrastructure, of course, we could think about digital technologies, health and pharma. We could think about digital technologies in manufacturing. We could think to global monitoring and surveillance of infrastructures, or even to a public administration that is fully functional and effective. So this is not necessarily only the future of a company. I think this is the future of any complex system, such as a society or a multinational group or even a small medium enterprise at different level. I think having those platforms in place, AI, HPC, cloud, wireless transmission network, would enable industrial pipelines to work much better than today. Think about agriculture. Precision agriculture is something that we will need to develop and face in most countries all over the world, simply because we don't have enough agricultural production to satisfy the needs, and also to improve the distribution of agricultural product that are maybe too many in some country and not enough in other countries. Imagine the improvement of any manufacturing industry. What we call today the industry 4.0 should improve substantially. Let me give you an example. Today, if you're in a big company, you have design, supply chain, manufacturing, engineering. So you have a sort of vertical silos, vertical areas that can be completely digitalized, but I would say in very, very few companies all over the world, those silos are transversely interconnected by a data warehouse. So an artificial intelligence system that essentially connect all the information and all the silos that essentially constitute the operation of the company. So today the effort, for instance, in Leonardo we're doing is to make it possible that the supply chain talks to the engineering, that talks to the procurement, that talks to the manufacturing. And this is the only way to optimize the production, to reduce the cost, to improve the quality of the products. And of course, I insist on that to be sustainable. I think people today are undervaluating, underestimating a very important benefit of the digital technologies. So AI, HPC, cloud, and so on and so forth. Those technologies can make our life, our production systems, our economy much more sustainable than in the past. And sustainability will be the ultimate challenge we are going to face as population in a planet that at the moment has 8 billion people, for a planet that is designed to host 3 billion people. So for sure, if you don't want to say simply we go back and we essentially lose the drive of the progress, nobody wants this, then we have to think to a progress that is more sustainable. And I believe HPC, digital technologies will be the tools to make things more sustainable. I insist on this point. I think it deserves a lot of attention and a lot of care by all operators, ourselves, operators in the companies, in the science, software, and code, the designer. So this is a very important point by which I want to close my speech today.
Okay, thank you, Roberto. Well, as you said, I totally agree with you. If we see, let's say, the value of companies in the stock market, and you check what was the situation 10 years ago and the situation right now, you can see that now much of the worldwide value is on company which do not produce goods. So physical goods, but the values, the market value. So there is an expectation also. I don't know if it is, let's say, on purpose or it is implicit in the way the world is transforming. Maybe we are not yet aware of what is happening in the history, but if you look at the value of the operator value companies, the most valued company are companies that are not producing physical goods. And this is a good news, because this means that we can have a much more sustainability. We can move from a society where the value, the intrinsic values, so the wellness was based on the burning carbon or oil or whatever, or nuclear, let's say, fuel, to a society where we are going to consume knowledge. And the knowledge, let's say, do not waste the planet, I would say. So I totally agree, and I think this is something we should probably, let's say, encourage the politician and all the society to move to. So to instead of buying and based on our, let's say, perception of wellness on goods, based our perception on how our, let's say, competence and knowledge is improving. Obviously, beside when we have solved the problem of feeding 8 billion of people in a world not designed to do so. So this is instead something that will remain as a challenge for the 2030 as well. I'm pretty sure. So now it's turn to Eric for taking his crystal ball and tell us what he saw or he is seeing in his crystal ball for what is a bio life science field. Eric.
So I'm actually going to second a whole lot of the things Elisa said. So in the interest of time and giving you a different opinion, I'm going to try to make a way broader approach. So in contrast to biophysics, where I am, if you look at life science in general, software is eating life science too. And one of the biggest themes, particularly in the US now, is the digitalization of life science, not just moving from test tubes to the computer, right? But as Roberto also spoke about, the whole strategic approach to data. We are starting to systematically collect data from every sample to physician to large-scale population studies and everything. So just simple things from all these tests from COVID, we're still not really sharing that between countries, which is, of course, a remarkable loss of information. And I bet the next time we get a pandemic, we are going to get better at this and projecting and deciding. As horrible as all these deaths are, right? The mere fact that different countries have chosen different paths, we will be able to learn from this. What worked, what did not work, how should we handle this next time? And the only way we can do that is by looking at the data and doing this kind of simulations too, but it's a completely different type of simulations than the ones we are doing now. Now, and I might regret saying this, but it's the very important thing. You should not put me or Elisa in charge of that, because the reason why we, I think, all have been reasonably successful is that our professors, advisors, they let us play around with all that supercomputing time. It was extremely expensive at the time. And we did completely different things that they would have done. And I think we didn't do too bad. But the point is that our students are just as smart. They will do completely different things from us. So we should not restrain them too much, but give them the time. We spoke about AI, right? There was an AI winter just 15 years ago where we had already proven that deep learning that learning artificial neural networks, it didn't work because they couldn't get enough data. And then people came up with this idea, funny, given this new hardware, very, very fast hardware that's available, what if instead of 3 layers, we try, say, 100 layers? And boom, suddenly it worked. And that was, of course, because suddenly they had access to 100 times more computational power than before. That was not a strategic decision. Nobody planned that when they built the hardware, but somebody was smart enough to realize, I might as well try it. And I think the same thing goes for all our industries. Many of the things I do, we're still focused on drug design. We're still focused on fighting disease, which is important. But I would bet that long term, we will get much better benefits from looking at what is that promotes health. It's much easier to cure that heart disease if we can prevent it when you're 40 by getting you to exercise more instead of trying to treat it when you're 75, because then it's kind of too late. We can only postpone the death a bit. And if we go beyond life science, right, policy decisions. Right now, we try to recover Europe. And of course, everyone wants investments everywhere, but I bet not all these investments are going to be equally productive, right? Which are the measures we should use? Why should we use them? And right now we don't know, because economics is still kind of based on science, but it's a bit of guesswork. So what if we could simulate these things? We could have an idea, we could test, and again, it's not going to be perfect. But if we could say that, oh, if we design the measures this way, we will get twice the return from it. And of course we're going to do it that way. We're not stupid, right? So I believe that promoting this way much broader ways, collecting data strategically, making sure that we develop faster by forcing people to share. Because again, short term, it makes sense for me not to share my data. That gives me an advantage. But if we all do that, we all lose. And that, of course, goes very much in the ESOF, like share the data, make sure we develop faster, make sure to build European advantage. Not necessarily in terms of IP, because remember, that's if you look at Google, Amazon, they don't necessarily lead by having the patents. They lead by developing faster than anybody else. And right now, I think Europe has a possibility to do that, but there is a ton of competition out there. So we have to move, and we have to keep moving fast.
Okay. Thank Eric, and thank all the speakers for this first round of, let's say, a question from my side. So I would like now to open the discussion to the public. If someone would like to ask question, okay, first. Hi, I'm James. From IIT. Please closer to the microphone. Yeah?
Yeah, okay.
Okay.
Okay, I'm Sauro Succi from IIT, and I'd like to thank the three speakers, two of which I know very well, Roberto and Elisa. I feel passionate about the topics that have been discussed, but let me ask the following question. We speak about synergy between HPC and artificial intelligence, say big data and machine learning. HPC is doing a great job, but still we cannot design an airplane by solving the full Navier-Stokes equation. We need models, right? And if I go to Eric's field, we still cannot move a protein for a second. We have to wait a lot, maybe 30 years, I guess. So the question is, how do you feel would machine learning help in 10 years from now design an aircraft without turbulence models, or moving a protein, say, instead of, I don't know, 100 microseconds, maybe 1 full second. There is a big hype, as you know, around machine learning. Some people, the most aggressive, even claim that we are useless, right? Of course, we are not. But the damage is there if we do not stand up. So my question is, how do you see this synergy developing for the next 10 years? I think it's a very important point for our field and for society in general.
Yeah.
And thank you so much again for the beautiful...
Because I too feel very passionate about this. I think this view is important, but I think this is also where lots of us went wrong 30 years ago, or 20 years ago at least. Many of us are theoretical physicists. And in one way, our nirvana would be, what if these equations in a computer could just predict everything? But the point is, when it comes to moving a protein for 1 second, doing that in a computer is pretty darn stupid, because we have excellent techniques that can already do that in the lab. So why should we try to do that in a computer? And I think part of the success in many of these fields is that we've realized that getting the computer to replace the experiment, that's the wrong question. But can we find the parts that are very difficult for an experiment to answer right now and add to that? And at least in my field, I feel that that's really where the experimentalists started to embrace computers, that we use the computers to answer different questions than we do experiments. They complement experiments. They don't replace them.
Okay, thank you. Thank you.
And,
that's
Elisa?
Yeah, very quickly, if I may. No, I think you're right. I think one of the things that we are going to learn is how to extract from all this amount of data also some information which can be rationalized. And there's a lot of room for scientists, somehow the old way, to extract from data this type of information. It's going to be an intermediate field that we can see already in some domains. For example, high energy physicists has a layer of people who working between data and models. But I think you're right. I think there's a need for computer scientists and engineers, but there's still a strong need to inject all this information about supercomputing data and so on into the education of scientists, and have top-notch scientists who know a lot about the science or the technology of their fields, and at the same time can benefit from that all and extract higher level information. That, I think, is one of the places where the evolution will take place, hopefully.
Thanks, Elisa. Roberto, if you have any comment to add?
Yeah, sure. I dare to give numbers. I think we need, in the next decade, 30,000 scientists, digital scientists or code scientists to be really inserted into the stream of the development of the science. But this has to be done in the proper way. It cannot be driven only by the universities, first of all. Most of us are coming from personal experiences, and then they have met problems, and then they have somehow we were forced to find new solutions, and then we landed on HPC, or we landed on deep learning or machine learning, whatever. I think we need a strategy. The strategy should start at school, and this is true everywhere in the world. I think only Korea and Japan are investing in this direction properly. We need to create new generation kids that are educated to be cross-disciplinary, code-oriented. I think we need a lot of lateral thinking in this in the future. We really need to put to put fields together that were not used to talk to each other. I mean, I'm thinking to the genomics. I have a personal experience in this field. Look, if one day we will have a sort of personalized medicine society, at least in the rich countries where it will be possible to have personalized medicine and personal therapies, this will only be possible if medical doctor, computer scientists, biologists, experts in vision, engineers will sit around the table and will develop a common strategy. I think we need to rethink entirely how to use this powerful tool that is the HPC and related technologies. We need an effort and we need many more brains for that.
Thanks, Roberto. I would like to give also my personal answer to that. My personal answer is a sort of, let's say, merging of the two things. It's useless to use AI where you have an exact model. So if you have a numerical model that is already giving you an high accuracy answer on the behavior of the physical system, there is no use to go for artificial intelligence. At the same way, we have data that are not yet represented by any theory. So in another way, artificial intelligence is a way to implement an implicit model of the data without knowing or without taking, let's say, or way to have let's say, underlying system of equation that describe the data. So the two things are in a loop to me. Well, so you can have a faster experiment or a synthetic experiment where you have a model, and in the other side, where you have data and theory, you can have an implicit theory and accelerate the cycle. So both together, to me, in the future, need to be used at the same time in what can be a sort of cognitive behavior of a digital system, not like artificial intelligence, because solving an equation, doing algebra is a cognitive, let's say, function of the brain as well, not only, let's say, deriving intuitive behavior across the data. So I think in the future we will see more integration, and a numerical model will not be abandoned to me. I have no intention to abandon numerical model. I don't know if this answered the question. Anyway, I have two questions from remote. One is a technical question to where the people can find a social media pointer to our speaker. So the name of the speaker, the web page, I don't know. There is a question that asking for contact point of our guest. I don't know if it is on the website. Probably yes, on YouTube you can find everything, and also the social media links to our guest. And there is another question to Eric from a student that asks what you recommend to a life science student in terms of let's say software engineering and competence he needed to develop, if I interpret properly the question, or he needed to combine in order to, let's say, have success in the field as you do in the field of biophysics.
So I remember when I was a student, I kind of longed back and realized how amazing it must have been at the start of the 20th century and living through the revolution of quantum mechanics, right, and everything. And then I had very much by chance the benefit of living through that in biology, life science, when we started to use computers. The cool thing that if you're a student now, I think you're going to have a chance to live through a third iteration here when we're all moving over to data. So if I was a student today, I would learn about data. But that is much harder than it sounds, because it's not just, if you just look at AI, you can't just learn everything and just throw data at the problem. You need to find out, how am I going to combine data with clear hypothesis? You're not magically going to get the data to say cure cancer for you. Because as difficult as we think mathematics is, biology is far harder. It's much more difficult to understand cancer than equations. So make a career where you combine a deep understanding of the value of data with an understanding of biology and hypothesis, and you're going to have an amazing career.
Yeah, there is, to complete the question was, the student was also asking if it is important to learn about the standard of software development to be successful in the field. So my answer is not the specific, then I will lead to Eric, but I have my own answer. I don't think it is really important to focus or to be stuck to a given standard, but understand that standards are a way, let's say, to share things with others without wasting in or being stuck in your own pot, let's say. So do not stuck with standard because standards are useful per se, but just because this is a way to share, at least in software developer, a methodology with others, and the standard will keep will keep changing in the future. We will see new standard and way of doing things, but it's important, I think, to be aware of some best practice, if you want, in software engineering. But this is my answer. I would like also to listen to Eric.
Yeah, I would largely agree there that standards, they change, but engage in a worldwide community. 90% of what I've learned is on-the-job training. But engage in a worldwide community, you will learn things, and this will also turn into a great career because suddenly you're no longer just dependent on, say, your local professor and department. You might have 10 people all over the world that know you and your work. So engage, share early. Don't worry about the fact that you think that your code might be bad. If other people use your code, you will improve it together.
Thanks.
So learn to code, but it's not everything.
Okay, thank Eric. We have another question from the audience. Yes, please.
Yeah, first of all, connected. Yes. First of all, thank you for this beautiful discussion and great speakers. I would like to connect this discussion on HPC and artificial intelligence and interbreeding in a way that now we are discussing for the future between our brains, high-performance computing, big data, and artificial intelligence. This connects us to the ESOF discussion that I organized on the extension of our mind and body into digital technology yesterday. So, let's start from the beginning. Our success as Homo sapiens species, the success that we are enjoying today, derives exactly from the interbreeding between our brains and tools that are external to our body. So we started with, as you know,
the hammer and
stone tools. Stone tools can fire, say, about 2 million years ago, and that created changes in our brain from which in one of the human species emerged complex language and other capabilities, mirror neurons, and the possibility of construct this big organism that was very successful. It was able to conquer the full planet, but it was not capable of using a small amount of energy. It used more and more energy, and this is continuing. Also with HPC and artificial intelligence, these tools need still a lot of energy. Now, there is our brain that is one of the components very important because for the theories, for example, we still rely on the individual brain and the social brain of the scientists, and then we need to interface this to HPC and artificial intelligence. But the brain is very, very plastic. Now, we learned to connect to all these new tools, and we, for the future, more and more are going to connect. But now, somebody like me is worried about the effect of our brain in terms of delegating to external tools decisions, not only, this that we've been talking today about HPC and artificial intelligence. So I would like to know from the speakers, from you, what you think about these aspects of for example, the risks. Is this community working on this topic concern or discussing about the risks. We know that artificial intelligence is already giving us problems in terms of social, political, and ethical things, using this methodology to influence people and read their emotions, use it for commercial and political things, as we've seen, like with the Brexit, Trump election, and so on. But there are also other aspects related to the individual cognition, given the plasticity of the brain. So I'm wondering if there is a bit of discussion on this topic.
The
and
answer,
I would like to know.
The short answer is yes, there is this discussion also internally, and I would like Roberto to answer this question, because there are a lot of discussion, especially because Leonardo is also a defense company, and especially in defense, these aspects are really crucial. So Roberto, if you have an answer for this concern about ethical things and decision, give up to taking our own responsibility in decision and leave machine to take for us these kind of things.
Yeah, okay, I'll try to be very quick. Look, somehow I believe that since Sapiens started to develop his development, he's been trying to augment his own performances. And the computers are nothing but another performance augmenter, pretty much like the caterpillar or the GRU or the lift or whatever you want. I don't think we are afraid of a caterpillar because it's stronger than we are, because we drive it. We should not be afraid of artificial intelligence because it is faster in making calculation than we are, because we drive it. I would like to remind that it is true today that a supercomputer can perform 10 to the 18 floating point operation per second. It's pretty much like the digital equivalent of the human brain is about 10 to the 17, 10 to the 18 operation per second. But every operation we do, it costs 5,000 less power than the electronic operation. We are driven by ions in water. The computer is electrons in a metal. We will never be matched because there is an impedance match. That this is a real problem. It's a technological problem. I think what we need right now is a regulatory frame. I'm not afraid of the supercomputer itself, or the AI itself. I think it's only a very powerful vertical machine, pretty much like the caterpillar or any other mechanical lift in terms of physical strength. This is computational strength, but it's essentially the same comparison, the same thing. I think we need, on the other hand, a clear regulatory frame, a legal frame, ethic frame. We need a code of conduct. We have it for car traffic. We have it for aircraft control. We need now for thinking machines, and they don't decide. I mean, I don't agree with the idea that machines decide. If you take 10 machines, you give them the same algorithm, the same boundary conditions, they will all conclude with the same decision. If you take 10 humans, the same boundary conditions, same situation, you will very likely get 10 different decisions. Pretty much because we have biochemistry. The machines have no biochemistry. So our decisional status depends, or our mind status depends on our hormones and our biochemistry. I think we should not confuse the science fiction with the science in some sense. And we should be ready, however, to give rules to this very potentially dangerous and powerful technology.
Thanks.
I would say, Carlo, if I may.
Yeah, Lisa, please.
One more.
20 seconds, 30 seconds.
The question is who drives the machines? And it's not obvious who drives them. And my conclusion is that the only way that we can have some control is not only regulation and so on, but also much more education of the people, starting from school, in looking into the things and understanding technologies and yes, getting everybody in there. Girls, not shared about technology, because otherwise you'll be out of the business, and more people really educated seriously into understanding technology.
So Eric, one word, if you would like to say your answer as well.
Yeah, I'm much more worried about humans than machines. Machines we can control. It's the humans that are dangerous.
Thanks. Wonderful conclusion. So I would like to thank again our speaker. It was a wonderful, I think, session, and a very let's say, important discussion and conclusion. I think people here and remotely have enjoyed, and they have a lot of food for thought about supercomputer and all this business and how this technology are changing our lives once for all, as it happened in the past with other industrial revolution. Thanks a lot again, and thanks to the public here in the room. I appreciate a lot, and from remote as well.
Thank you, guys.
Thank you, everybody.
Thank you.
Thank you.